So let's continue with our study of polynomial rings. In the last video, I talked about what polynomials over a ring are. So let's quickly recall that. And then today we will discuss that, and we will make it a polynomial ring. Okay. So if R is a ring, R is any ring. Remember, we used notation R square bracket x, where x is a variable. Okay. So remember, I told you that variable means it's just a symbol, it has no meaning. So it is just a symbol. So this is the set of all polynomials over R. So I told you what those are. So these are expressions of the form. So this is like this: a(n) xn plus dot 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 a1x plus a0, where n is a natural number and ai's are all elements of the ring R. Remember that we can choose, we have to take all polynomials. That means we have to take small n for every natural number and consider all polynomials with all the coefficients being any elements of the ring R. So now the next thing is we want to give a ring structure to Rx. So this is our next goal. What is a ring structure? Remember from the definition of a ring that we gave some time ago, a set is called a ring if it has two operations. We usually call them addition and multiplication. Under addition it has to be an abelian group, multiplication has to satisfy some properties but it need not have inverses, and addition and multiplication have to distribute. So there is one natural way to add and multiply polynomials. So let us recall what that is. So to add polynomials, so in order to make Rx a ring, we have to define addition on Rx and multiplication on Rx. Addition is the something that you can guess. So take two polynomials. So basically to add, I will write it like this first. To add two polynomials, we simply add, let us say f and g are elements of the polynomial ring, in other words they are polynomials. To add f and g, we add like terms. Okay, so I will explain this. So we add like terms. So what does this mean? So when I say like terms, that is we add monomials, coefficients of monomials of same degree. Okay, so I do not know if I mentioned this, but if you have a polynomial something like a(n) xn plus a(n minus 1 xn minus 1, this is a polynomial, meaning lot of terms. A single term of this is called a monomial. So this is a monomial, this is a monomial, this is a monomial. So these are all monomials. And what is the degree of a monomial? Degree of a monomial is, this degree is n, this degree is n minus 1, this degree is 1, this degree is 0. Remember, degree simply stands for the exponent of x. So each monomial has a degree to it and we add coefficients of monomials of same degree. So in other words, so it is actually very easy to understand this. So I will just give you an example to describe this. Let us say f is 10x5 minus 5x squared plus 2x plus 8. Okay. So you can think of this as a polynomial with integer coefficients, and let us say g is 7x power 6 minus 8x power 5 plus 5 x squared minus 8. Okay. So, what would be f plus g? So, f plus g would be, so you remember you have to add like terms. So, you compare terms, the largest degree that you have in x in f is 5, largest degree you have in g is 6. So, comparing order degree 6 monomial, there is only one, so that is 7 x power 6. Now, to add the next monomial, x power 5 is common to both, so it will be 10 x 5 minus 8 x 5. So, this is 2 x 5. Okay. So, this is the, we add coefficients, we add the coefficients of like terms. So, this is similar to this. Okay. So, 10 plus minus 8 is 2. So, that is 2 x 5. There are no other terms until x squared. So, x power 4 is not present in both, x cubed is not present in both, but x squared is present in both, and the coefficients are minus 5 and 5. So, this is just 0 x squared. So, I am writing it now, but we do not need to write it in general. And now next we have to compare x terms. There is x in f, no x in g. So, that is just 2 x, and we have 0. So, f plus g is actually just 7 x power 6 plus 2 x power 5 plus 2 x. Okay. So, that is f plus g. So, you understand how to add two polynomials. We simply add like terms. So, we can formally write the definition as, let us say f is a n x n, a n minus 1 x n minus 1, a 1 x plus a 0, g is let us say b m x n, b n x m n, b n minus 1 x n minus 1, b 1 x plus b 0. And in order to write the same n here, I am allowing a n or b n to be 0. So, here of course, if I write like this, f will be 0 times x power 6 first term. So, a n on b n can be 0. So, then f plus g, one of them will be 0 maybe, not both of them of course. This will be a n plus b n x n, a n minus 1 plus b n minus 1 x n minus 1, so on, a 1 plus b 1 x plus a 0 plus b 0. Okay. So, this is a very natural way to add polynomials. So, this is the addition, and I will simply assert here that under addition R x is an abelian group under addition. Okay, this is very easy to check. The coefficients are inside a ring. So, the coefficients are in a ring which is an abelian group under addition. So, coefficients satisfy group properties, and here to add two polynomials we are really not worrying about x. X is just like a placeholder. X tells us what is the degree, that is all, and essentially we are adding elements of R. We are adding elements of R in various degrees, because addition and in R satisfies group axioms, addition in Rx also satisfies group axioms. What is the 0 element? Is the 0 polynomial, right. So, 0 polynomial has all coefficients 0, that is the 0 element. What is minus of f of x? So, if f is like this, if f is a n x n plus a n minus 1 x n minus 1 and so on, what is minus of f? That is clearly just minus a n x n minus x n minus a n minus 1 x n minus 1 and so on, minus a 1 x minus a 0, and associativity certainly holds, and you have in other words a group. So, so far so good, right. So, we are trying to give a ring structure to R x, we have defined an addition, and under that we see that it is an abelian group. It is an abelian group, right, because f plus g is g plus f. That is because the addition of elements of R is commutative, and adding elements in R x, in other words adding polynomials, is just adding elements of just like adding elements of R. So, this is okay. So, it is an abelian group. So, next what is multiplication? So, next we want to understand what is multiplication on Rx. So, this is also very similar and we slightly more technical, but you have to get used to this is not difficult. So, we first learn how to multiply two monomials. So, and that is natural. So, if you have x power I and x power j, how do you multiply them? You simply take it to be x power I plus j. On the other hand, if you have a x power I and b x power j, remember a and b are elements of the ring. So, a x power I, b x power j, I will define it to be a b x power I plus j. Remember a b is actually multiplication in the ring R. So, this is multiplication in R, because a and b are in R, I can multiply them because R is the ring which has multiplication. So, this is multiplication in R and x power I times x power j is x power I plus j. Now that we know how to multiply single monomials, we can simply generalize this to define multiplication of any polynomials. So, I will write an example first and that will tell you how to multiply, and then I will write the formal expression for multiplication. So, again very simple example. So, let us say you have f is 2x squared minus 3x plus 5. I am just taking arbitrary polynomials, and you have 3x cubed minus 3, let us say. Okay. So, it is just like adding, you add the way you add numbers in when you add two numbers and multiply with another number. So, how do you multiply f and g? So, what we want to do is 2x cubed minus 3x plus 5 times 3x cubed minus 3. So, how do we multiply? So, I will first think of this 2x cubed and multiply this polynomial. So, what is 2x cubed times this polynomial? I will multiply one monomial at a time. So, 2x cubed times 2x, so this is 2x squared. 2x squared times 3x cubed is, because of the rule that I wrote here, it is 6x power 5. Next I will multiply this with minus 3. So, I get minus 6x squared. So, I have taken care of 2x squared. Next I look at 3x. So, minus 3x times 3x cubed. So, that will give me minus 9x to the 4th, okay, and then minus 3x times minus 3, that will give me 9x, and finally I have 5 times 3x cubed. So, that is 15x cubed, and minus 5 times minus 3 is minus 15. So, now all you need to do is combine like terms. So, that for example, here are there any like terms? Actually there are no like terms here. So, you can just put the degrees in the decreasing order. So, you get 6x5 minus 9x4, but if in general if you have x square may appear twice, in which case you will just add the coefficients of x squared. So, in this case what we have is minus 9x4 plus 15x cubed minus 6x squared and plus 9x minus 15. So, hopefully this gave you some idea of how to multiply polynomials. Okay. So, all you need to do is repeatedly do this multiplication of single monomials. You have several monomials in the first polynomial, you have several monomials in the second polynomial, and you can multiply a monomial at a time. So, what would be the general formula for multiplication? So, general formula. So, for that let us write f as a0 an xn plus an minus 1 xn minus 1 a1x plus a0, g is bm xm bm minus 1 xm minus 1 all the way up to b1x plus b0. So, let us say f times g, I want to describe f times g. What is this? So, f times g, I will first write the general, so the largest degree term will be mn. Okay. So, p mn x, sorry, this is m plus n because xn times xm is m plus n plus p m plus n minus 1 x m plus n minus 1 all the way up to p 2 x squared p 1 x plus p 0. So, I am using pi's to denote the coefficient of f g. Now, I need to tell you how to find the coefficients pi, because in order to tell what f g is, I need to simply tell you what the coefficients are. These coefficients will be described in terms of the coefficients of f and g. So, what is p k? So, for any k, so let me write it like this: for k between 1 or 0 and m plus n, p k is equal to, okay. So, if I will write down the formula, you can quickly check using the example and the definition of multiplication of monomials that this is correct, and this is fairly straightforward. In order to get x power k term in the product, we have how to get x power k term in the product. We can multiply two monomials in f, one in f, one in g, whose degrees add up to k. There might be several such choices. For example, to get x power 5, you can multiply x term in f, x power 4 term in g, x square term in f, x cube term in g, x cube term in f, x square term in g, and so on. So, we have to add a I times b j, we have to multiply the coefficients of the corresponding terms for every I j which add up to k, right. So, this is the expression for coefficient of f g. So, in particular we know p 0 will simply be a 0 b 0, which is not surprising, right, because to get the constant term of f g, you must set there is only one possibility, you have to multiply the constant terms of f and g. Similarly, what is p 1? To get the linear term, degree 1 term of f g, you can multiply the linear term of f with constant term of g, that will give me a 1 b 0. Similarly, I can multiply the constant term of f with linear term of g, so and so on. And finally, what is p m plus n? This is simply a m or a n b m, okay. So, this tells me how to get all the coefficients of the product, and again I will simply assert these without proof, which can be checked easily, and these are not difficult and they are not very illuminating to check. So, I will simply write that there is a multiplicative identity simply 1. So, we denote multiplicative identity anyway by 1 in any ring. So, 1 will continue to be multiplicative identity here, because if you multiply any polynomial by the constant polynomial 1, you get 1, and multiplication is commutative, right, because okay, this requires a little thinking, but ultimately because multiplication in the base ring R is commutative, multiplication in the polynomial for polynomials also is commutative, it is certainly associative, multiplication is associative, and finally addition and multiplication distribute, okay. This is also again ultimately because addition and multiplication distribute in the ring R. So, they distribute in the set R x also. So, the conclusion of all this is, I will write this as a preposition. So, hence we have a preposition R x with the addition and multiplication defined above is a ring, okay. So, I have not proved this, I will not prove this, I will only write this, and we will obviously use this a lot. This is an important example of a ring for us. So, this is a ring with the addition and multiplication defined above. We can add and multiply polynomials. So, it becomes a ring, it has all the required properties, and moreover R can be identified with the subring of R x consisting of constant polynomials. So, what are constant polynomials? Constant polynomials are polynomials of degree 0. So, constant polynomial is degree 0 polynomial. Okay, so, inside R x you have degree 0 polynomials. So, these are just what is a degree 0 polynomial? So, it is just of the form a 0, right, with a 0 in R. So, R can be identified with the set of a 0 in R x. Okay, this is a very obvious statement, because a constant polynomial has no x in it, all the data that is required to describe a constant polynomial is just a 0. So, this is a subring of R x that one can check quickly, because you can add elements and you will land here, and you can multiply, you will land here, 1 is there and so on. So, this is a subring and R can be identified with this. So, this is important for us. We have constructed a new ring starting with a ring R, we have constructed a new ring and we called it the polynomial ring, and the new ring contains R as a subring. Okay. So, this is an important point. So, now let us study these polynomial rings a little bit more. I want to introduce an important concept here. We want to be able to divide polynomials. So, in R x we can sometimes, I will write, not always, divide polynomial. So, what is it that I want to do? Okay, so, I am going to quickly do this. I will not write the formal procedure, I will just explain the procedure by an example. This is the usual division of numbers, it is the same procedure that you all know very well. So, the statement is given, so R and F are, R is an arbitrary ring, R x is the polynomial ring over it. So, given two polynomials f and g in R x with f, let us say, monic polynomial. So, I do not know if I define this. So, what is a monic polynomial? So, I will quickly define what is a monic polynomial and then I will continue this. Definition: a polynomial is monic if its leading coefficient is 1. Okay. So, what is the leading coefficient? It is the coefficient with the largest degree. So, for example, f equals 2x squared plus 3x plus 1 is not, let us say, inside zx, is not monic, right. Its leading coefficient is 2. On the other hand, g is x power 5 minus 6x plus 2 is monic. And what about h? H is 3x squared minus x cubed plus x 4 minus 2 is also monic, right, because even though I have not written them in the correct order, the leading term is this. Leading term is by definition the term with the largest degree. So, here the leading term is x power 4 and its coefficient is 1. So, it is monic. Okay. So, this is a side definition. Now, let us come back here. Given two polynomials f and g with f x a monic polynomial, we can divide g by f. What is the division? really mean? It means the following: there exist unique polynomials Qx and Rx such that we can write Gx as Qx times Fx plus Rx, and the Rx obviously stands for the remainder for this division. We have two possibilities: either Rx is 0 or Rx can be 0, or we can define the degree of Rx if it is not the 0 polynomial. Remember, degree is the largest degree that appears in the polynomial, must be strictly less than degree of Fx. So, I suggest that you think about this carefully. This is exactly what we mean by division for integers. For example, if you have two integers, we can divide one by the other, and we can, that means we can write it like this. There the remainder is either is always strictly less than, it is a non-negative number, it is either 0 or it is positive. If it is positive, it is strictly less than what you have divided with. Okay. So, that is all. So, we can always do this. So, in order to explain, I mean you can prove this, but that will take me, I mean that is unnecessary to do this, you are all familiar with this. So, to explain what really happens, I will simply just do an example. Okay. So, quickly let me do this. So, what we will do is we will take f to be. So, I have written this here, x squared plus 2x minus 1, and g to be 3x4 minus 7x cubed plus 4x squared minus 10x or plus 10x minus 2. Okay. So, let me just do an example. So, here I want to divide this. So, this is the usual Euclidean division algorithm. So, you have x squared plus 2x minus 1 here, 3x4 minus 7x cubed plus 4x squared plus 10x minus 2. So, I am going to write the terms here. So, first I want to divide 3x4 by x squared. How do you do that? That is simply 3x squared. Here you see why I need the leading term to be 1, because if it is not 1, I may not be able to get 3 that I want. So, I will describe this again in examples. So, x squared times 3x squared is 3x4, you have plus 6x cubed minus 3x squared. So, now you subtract, right. So, in other words you change signs. So, you cancel this. So, what you have is minus x cubed. So, let us see. Yeah, sorry, this is actually plus becomes minus. So, 7 minus 7 minus 6 is minus 13 x cubed, and you have 7 x squared, and you can also bring down 10 x. So, next you want to cancel minus 13 x cubed. So, you get minus 13 x here, right. So, minus 13 x. So, that is minus 13 x cubed minus 26 x squared plus 13 x. So, now you subtract again, what you get is 33 x squared. So, you subtract minus 3 x is what you get, and you have a minus 2 from before. So, you write minus 2. Now, you want to cancel 33 x squared. So, what you get is 33, just 33. So, you get 33 x squared plus 66 x, right, 33 x squared, 33 times 2 x is 66 x minus 33. Okay. So, then you subtract again. So, this minus minus plus. So, this will cancel. What you have is minus 69 x and plus 31. So, that is all. So, this will be Q or this will be R and this will be Qx. So, we have written the polynomial f g as f times f x times, so g x I will write g x as f x times q x. I am mainly interested in the remainder. So, remainder is minus 69x plus 31. Okay. So, this is the remainder, and remember what is the property of the remainder? It is either 0, in this case it is not 0, or its degree is strictly less than degree of f. What is the degree of the remainder? Is 1, which is strictly less than degree of f, which is 2. This is not surprising, right, because we can always continue the division procedure until the remainder is of smaller degree, because if it is bigger degree, or if it is at least degree equal to degree of the polynomial you are dividing by, you can continue. So, you will go until you have a remainder of smaller degree, or you get 0. So, I hope this is clear. The procedure is just very simple. So, we can always divide one polynomial by another monic polynomial. So, I will stop this video here, and in the next video we will discuss a little bit more about division inside polynomial ring, and we will study a few more properties of the polynomial ring. Thank you.